So I realize that I am the guy standing between you and beer on a warm Tuesday evening in August. And I kind of misjudged the slide deck because I wasn't sure it was 20 minutes, so I kind of put a bit more content in there. So what I'll do is, I'm going to rush through some of the slides, and you can hang around and ask me questions afterwards if you need that. So just a little bit about me. I'm one of the founders of StorageOS. We're building software-defined storage systems that run in orchestrated environments, cloud-native environments. I'm also recently appointed the co-chair of the CNCF Storage SIG. The Storage SIG is a new creation. We used to be called working groups before, but the storage SIGs are now here to help scale the CNCF. So as you're probably aware, the CNCF are the guys behind Chircop and Kubernetes and a variety of other projects. And we're now over 400 vendors and companies are part of the CNCF, and there are probably about 800 end user organizations too. So the SIGs help the CNCF with some of the work that we're doing in terms of selecting projects and identifying technologies that can help with the different CNCF technologies. So I'd really suggest you have a look at our page there. There's all the minutes of all the previous meetings, and the meetings are public. We often have lots of interesting project presentations in those meetings. So what I want to talk about today is cloud-native storage and why this is important. So the obvious thing is there is no such thing as a stateless application, right? So we often talk about containers being stateless and this sort of thing, but at the end of the day, the state has to be stored somewhere. And while we want to have the benefits of containers, and containers make your applications portable, and Kubernetes abstracts away your infrastructure, we need to have a storage solution or storage solutions and technologies that can work in that sort of environment. And what do we mean by cloud-native technology? So the first important thing is that cloud-native storage is going to be application-centric. So today, most storage systems are presenting storage to operating systems or VMs. And what we really need is storage that's being presented to applications and can move around with the applications as the applications move. In a similar way to all the benefits that you've already done to make your applications cloud-native and made them portable and able to run on-premise and in the cloud, etc. You also want your storage to be platform agnostic and to have the right abstraction layers in there so that you can consume that storage from different places. Of course, it's really important that storage is declarative. So we go through a lot of effort with things like with orchestrators and Kubernetes to be able to say, this is what makes up my application. I can say it needs these containers with this software, with this network port, with this routing configuration. But you should also be able to say, and I need this type of storage with these type of attributes. And for that to happen, obviously, the storage needs to be API driven. And I put agile, and everybody will roll their eyes because it's cliched. But what I mean by agile there is, in cloud-native environments, there are lots of moving parts. It's much more dynamic than a traditional environment. So nodes come and go, you're probably scaling dynamically. And you need to have a storage system that can provide the availability and can provide the performance and can provide the durability and reliability in an environment where everything is changing. And let's not forget that agility also implies things like security, because you typically have multi-tenanted environments. So, in summary, cloud-native storage makes your apps better. So what we did, the cloud-native storage landscape is huge. There are dozens or hundreds of projects and lots of vendors providing lots of different functionality. So what we decided to do was, we decided to write a white paper that would actually help people to understand what goes into a storage system. And the white paper is fairly long. It covers the things that allow a developer or a DevOps team to be able to figure out what type of storage they need for their application, because we're kind of evolving from sort of an environment where in the past, an application developer was given storage by an infrastructure team, but now they're actually able to define what their application needs and what type of storage they need. So we define things like the attributes of the storage, the various layers in the storage system, and how they get orchestrated and the management interfaces. It is a 40-page doc. I'm not going to go through all of it. So this is the short version. So inside the storage system, we have a number of different interfaces on how you consume the storage. You have multiple layers of functionality. And effectively, you're choosing a storage system and you're designing a storage system based on a number of attributes. So things like availability and scalability and performance. Because at the end of the day, what you want to do is you want to choose a storage system that's going to match what your application needs. And those attributes can be measured in multiple different vertices, I guess. So things like availability is often thought about, you often think about how do you replicate, for example, and what type of redundancy is the storage. But we also need, because this is cloud native, we also need to figure out things like how you do failovers between nodes, how you move data between nodes. And again, things like scalability often talks about the number of nodes, but you might want to measure scalability in terms of the number of operations that you're doing or the throughput, or indeed the number of clients that can access that system simultaneously. Similarly, performance is measured in, again, different metrics. So we have things like databases or message queues, for example, that might be really latency sensitive. But on the other hand, if you're doing analytics or something like that, maybe the only thing that matters to you is throughput. The other big thing, because in cloud native systems, you kind of have a proliferation of a variety of distributed systems. Those systems, you need to understand what the consistency model for those processes are. So consistency can mean different things to different people, but ultimately it's the difference between the time it takes for something you commit to actually be registered and be readable on other systems. And that is a really important factor, because it does affect some of the other functions, like often you have compromises between availability and performance based on different consistency models, but it can also affect things like durability and your ability to recover, say, from power failures or outages like that. And finally, you also have to keep in mind how you actually deploy and instantiate the storage system. So you have traditional hardware solutions, which obviously are the things that you know and love in standard data centers, but obviously that limits portability. You have software solutions that are extremely portable, and they tend to be more platform agnostic, but they also tend to be based on shared nothing architectures, which give another set of problems or another set of challenges to overcome. And you've also obviously got cloud services. So each cloud provider typically offers 5 to 10, maybe even more different storage services. So how do we access storage? So for the most part, people tend to think of storage in terms of how they access the storage. So you have workloads, and you have an orchestrator that's orchestrating the storage system. But the way that you access the storage is what we call the data access interface. And we kind of we did a lot of thinking here. Now, storage can mean the typical things, a file or a storage block device, for example. But actually, more and more in cloud native environments, storage is actually can be anything where you need to persist data, right? So it can be a database, it can be a key value store, it can be an object store too. Now, it's probably fair to say, though, that a lot of the focus and a lot of the maturity in orchestrated workloads has gone into managing volumes. So today, most of the abstractions are how do you get a file system access into your container? How do you get shared file systems access into your container? And while there's a huge plethora of services for object stores and key value stores, etc., most of those things don't have the declarative abstractions to be able to say, I want to start up a new object store, for example, or I want to create a new bucket of space. Now, when we were writing the white paper, we also kind of did a lot of thought to kind of say, what do people actually expect when they think of these different access interfaces? Now, for the longest time, access interfaces used to define the primary criteria for your storage. So if you wanted something that was really low latency, you'd go for block storage. If you wanted something that where you had a shared workload and you had multiple things that needed to access the same files, you'd choose a file system or some sort of shared file system. And if you just had this, huge data lake with lots of information, you'd probably choose an object store. And for the most part, that kind of defines things like your latency and your sharing capability and some of the performance characteristics. So what I'm going to say, though, is that doesn't count anymore, because most storage systems today are formed of a number of different layers. And the different layers can be exposed as any number of data access interfaces. So you have file systems that are built on object stores. And so you have the sharing capability of a file system, for example, but you have the latency attribute, the high latency attribute of an object store, for example. And there are all sorts of really quite complicated layering. So you can create block stores out of file systems. So Gluster has the capability of doing that. You have Ceph, which is an object store, which also shows up as a file system. So it's kind of so what we kind of said was, okay, so the data access interface isn't how you measure a storage system anymore. It's important. It's one of the things that contributes to the attributes, but it isn't the only thing, because we have a bunch of different layers. And understanding those layers is effectively what you need to understand for your application. So at the very top, you're going to have an orchestrator or your host or an operating system that's doing things like volume managers, or perhaps something like a service mesh like Istio, which is controlling what you access and how you access it. You also have to consider the storage topology. So there are a number of different storage topologies, and this has huge effects on things like availability and performance. So on the one hand, you have centralized storage architectures. So these are typically characterized by hardware that has proprietary interfaces, and they're designed to scale up rather than to scale out. And they're really good at doing low latency, but they're also really expensive because you have to scale them up. You then have distributed systems, which are typically made out of, have software options, or they can be scaled out using commodity hardware. They have much better cost characteristics, and they have much better scaling characteristics. There are a variety of systems, including databases and object stores, that use sharded technologies. There are also things like database projects like Vitesse, for example, that use sharding to scale out MySQL databases. And similarly, things like Redis and other things like that. However, obviously, managing sharding has its own complexity, and that's something that needs to be concerned. So each of the different topologies does affect, we already said that it affects things like availability and scalability. I'll leave this up on the screen. We can send this out afterwards, and you can read it in more detail on the website. The other things that affect a lot of the attributes are the data protection. So most applications have some sort of dependency in terms of their architectural patterns that the storage is providing some level of availability. So a lot of the designs on how an application recovers in the event of, say, a node failure or a component failure or a network failure is based on the availability of the data somewhere else, and that implies a dependency on that storage. So At the most basic level, you have things like RAID levels or mirrors, where a storage system is actually just making copies of data or using some sort of parity algorithms to spread the data across a number of disks to allow you to survive disk failures. As one level above that, we have technologies that use erasure coding. So erasure coding is kind of a more advanced form of parity, and this allows you to split the data into multiple little chunks that can be spread around the whole network. And this gives you much higher durability capabilities, because you can now lose multiple nodes, for example, or multiple hard drives. Of course, the calculation overhead of splitting all of those chunks and the cost of sending all of those chunks over the network doesn't mean you have high latency overheads, which means that erasure coding is often found in things like object stores. And then if you want to have distributed reliability, but you can't take the overheads of something like erasure coding, then replicas are typically the answer, where you have copies of the data on more than one node. The storage system will also provide a bunch of data services, so things like replication across data centers, or providing point-in-time copies with snapshots and clones, or indeed securing your data by using some sort of encryption. And of course, we mustn't forget the physical layer, which ultimately does impact a lot of the durability and performance characteristics of the storage system. Pardon me. So we talked about the client-native storage needing to be declarative. So what does this actually mean in real life? So the data access interface is that little column C in the picture. So effectively, that's how workloads talk to the data plane in a storage system. But the orchestrator, the Kubernetes, needs to be able to say, I want this type of storage. I need that storage here. It needs to be this size. It needs to have these attributes. So the stuff that you declare, in your pod, in your storage classes, and there are a number of different interfaces that exist, and I'll talk about those in a second. But ultimately, we have two major types. The first type is where a storage system is, natively integrated with an orchestrator. So they will use native interfaces with Kubernetes or some of the CSI drivers, for example. But there's also a variety of frameworks and tools that integrate orchestrated workloads with the actual storage system. So an example of that, and it's also a CNCF project, is Rook, which is actually orchestrating Ceph on the back end, and is kind of taking Ceph, which was sort of designed pre-Kubernetes, and taking those API connectivity from Kubernetes and translating them into the equivalent Ceph functionality. So there's a number of different options on these interfaces. It's probably worth saying that today, most of the focus from all the storage providers and the different container orchestrators is CSI. CSI is the container storage interface, and it's kind of another one of those API standards, like the CRI, the runtime interface, and CNI, the network interface. And this is basically an abstraction layer. So CSI effectively provides a standard API and a standard driver mechanism where Kubernetes can talk to a CSI driver, and that CSI driver has a number of different abstractions that talks to the storage system. So the storage system can now be effectively orchestrator agnostic. All of the standards, CSI is the future, because things like native drivers were becoming extremely unwieldy. So, for example, StorageOS was one of the first organizations to build native drivers for Kubernetes. And we actually have our code, our drivers mainlined into the Kubernetes code. But that does mean that every time we need to do a patch, or we discover a bug, or some new functionality needs to be added in, well, you kind of have to upgrade your whole version of Kubernetes. And that is not, that's not practical. So the whole concept of CSI means that we've now kind of got the concept of a driver just like any other driver in any other operating system, and we have that functionality there. So I would strongly recommend that you have a quick look at the SIG storage. We have public meetings every couple of weeks. There's sort of 30 odd vendors there, but there's a lot of independent people and end users there too. And we would really love to have your feedback. So we put a little survey together to kind of figure out what you guys are using most, where your pain points are, and this allows us to help prioritize and focus what we work on next in terms of the projects that we put together or the content that we put together to help. Now, my marketing guys would kick me in the ass if I didn't say a little bit about StorageOS. So I've just got a couple of slides and I'm going to say this. So StorageOS actually is a cloud-native storage platform. We are actually deployed as a container. We're platform agnostic. We don't have any proprietary dependencies on kernel modules or hardware, which means we can be deployed anywhere you deploy your applications. And we abstract away storage pools out of your clusters and create a simple way to dynamically provision storage using the CSI drivers and providing a rich set of functionality like encryption and replication and compression. Within the StorageOS container, we have both our control plane and our data plane. The control plane provides all of the health endpoints and the availability to understand the state of the cluster and understand the config of the cluster. And the data plane provides all of our virtual storage interfaces, so those data access interfaces we were just talking about, providing transparent failovers, but also things like inline encryption and inline replication and inline compression. And we kind of do this by creating these virtual storage pools that can use any of the underlying storage on any of the nodes in your environment. So it doesn't matter whether you're running this using physical disks on bare metal or virtual disks in VMs or cloud storage like EBS, etc. in your cloud instances. We can just take all of that storage, create a virtual storage pool, and then create your dynamically provisioned volumes out of that. And that's me.